So, thanks very much, folks. I'm going to introduce Cory Lueninghoener. He leads the High Performance Computing Design Group at Los Alamos National Lab. He's going to talk about applying SRE ideas in a more traditional operations environment. So he's going to talk about error budgets, downtime budgets. I guess it's a very different environment where you have jobs that can run for days to weeks. Anyone who's had experience with HPC, it's a great idea to apply an error budget, but what happens if I take down a large part of that cluster? And how do I do that when I have 60,000 nodes in the one machine? So, Cory, I can't wait to hear.
Thank you. So yes, I'm here to talk about, to change gears a little bit and talk about something a little bit different than what we've had at the conference so far, high performance computing, and taking some SRE ideas and applying them in a more traditional operations environment. So first off, a quick who am I? Cory Lueninghoener. I'm the HPC Design Group Leader at Los Alamos National Laboratory. I do system administration, configuration management, lots of scalable system design, that sort of things. I was one of the co-chairs for LISA 2015. If you were over in Washington, D.C. last fall, you might have seen me standing up here waving my arms on a platform also. And there's a whole bunch of social media links if you like that sort of thing. So where do I come from? Los Alamos National Laboratory, it's a research institute over across the pond in the US. It does a lot of different types of scientific research. So physics, climatology, biology, sociology, chemistry, astrophysics, all kinds of things. And there's a lot of high performance computing that goes in with this, where they're running simulations to see what happens in these various fields. And so that's the main part of what I'm going to talk about for a moment. I'll start out with a little review of what high performance computing is, because I know it's different than here. At its basis, it's just the discipline of using hundreds or thousands of computers connected with a high speed network, maybe sharing file systems to run simulations and get things done. There's two ways to look at that to start out with, the systems and the applications. So we'll split that into two pieces to start out with. This is what a typical HPC system looks like, a cluster. There's a bunch of compute nodes up there in the upper left-hand corner. That's where all of the work happens. Some I/O nodes down here that act as routers so that the compute nodes can talk to various file systems or anything that's outside of the cluster. Down here in the lower right, some login nodes. That's where people actually log in, compile things, submit jobs, do the actual work. Well, do the actual pre-work before submitting it to the compute nodes. In the middle there, some management nodes. Those are running the configuration management tools or whatever automation tools we have, schedulers, anything that we need to actually manage the system. Monitoring goes on there also. There's a couple networks in here. There's the management network, a standard 1 gig network, nothing special. The high speed network is one of the things that kind of defines why this is a cluster. This is a special dedicated network, low latency, high bandwidth for making these compute nodes talk to each other quickly. This is also the thing that makes things difficult with these, as we'll see later on. There's also the campus network where people log in and actually do things, and down the lower left-hand corner there's some file systems. NFS is usually the serial file system where things like home directories are stored. And then a parallel file system, Lustre, is the one that we normally use, but GPFS, Panasys, a bunch of other things that the people may have touched here also show up there. So for reference at the lab, we have about 20 clusters that we manage, ranging from a couple hundred to tens of thousands of nodes, about 36,000 compute nodes total, about 1.2 million compute cores, and about 110 petabytes of Lustre storage across a few file systems. And this is all housed in 3 machine rooms that we have, takes up about 5,000 square meters. So that's the general scale that we're looking at. Meanwhile, this is what a typical HPC application looks like. It actually looks more like code like you'd see normally, but this visualization gives a good indication of what things are going on a system and why things are difficult. So this is an astrophysics simulation that we're looking at, modeling the center 1 light year of our galaxy. You can see there's a mesh laid over the whole thing, and that you can look at that as splitting the work up among different compute nodes. Each one of those little squares would be assigned to one compute node. There's different sizes to the mesh over in the left-hand side. There are some squares that are really big because there's not much happening there. In the middle, right next to the guy's head in there, there's a feature that they're very interested in, so the squares are very tiny. And so you can see it's not evenly distributed. And meanwhile, all of these different squares need to talk to each other. Particles might be moving in between them. There's communication that has to go on in between these. And since these are compute nodes, this is this many compute nodes that you can see here. I haven't counted how many are actually there, but a lot of them need to be able to talk back and forth to each other all at the same time. This simulation may run for a few hours or a few days or a few weeks even, with all of those systems needing to do that sort of work. So a typical jobs at our site, between 64 and 64,000 cores. It's about 4 to 4,000 nodes. Running between 1 and 24 hours for us. We tend to have a limit of 24 hours to make people resubmit jobs multiple times to help with the throughput. About 3,000 users, around 300 active at a time, but 3,000 total. And about 6,000 jobs will run in a typical day across all of the systems. So now, comparing that to what we have been talking about for the last couple of days here, there are some notable differences between HPC and web engineering, the traditional SRE discipline. So instead of lots of small, redundant, resilient sort of jobs, there's a smaller number of really large, tightly coupled jobs. Instead of millions of transactions in a certain unit of time, we'll have tens or hundreds. Instead of millions of customers, we'll have a small set of domain experts, scientists. But there are a lot of similarities too. Very large scale systems, very small scale operations or admin or SRE or whatever you want to call it teams. And lots of monitoring and metrics gathering to do during all of this. So some of the metrics that we gather, some of them are typical monitoring stuff that anybody would think of here, node health, what the temperature is, what the load is, all of that sort of stuff. Outages, whether they're planned or unplanned, so normal things go on. But then there's some HPC specific things that we are collecting also. What the health of the high-speed network is, how fast it is, what the injection bandwidth looks like, a number of different things. The parallel file system health, how fast it's going, how much free space there is, what the disks are looking like. The depth of the job queue, whether people are submitting jobs, how long they're sitting there, who's doing it, how long they're running. And utilization, when jobs start, when jobs end, who owns them, and how big they were. So utilization specifically is an important metric. These clusters are built to run jobs, and so we want to actually get utilization out of them. This is a graph that we look at to see what things are looking like on this set of systems. On a typical HPC system, around 80% is actually pretty good utilization because you have to wait. If you have a really big job and it has to schedule that, you have to wait for the machine to drain enough nodes that can start and everything. So you never really expect to hit like 100%. So 80%, that's a good place to be. If you're above that, great. If you're below that, start thinking about what's going wrong. You can see two of these clusters don't have anywhere near that. The top one, Cielito. It's a test and development type system, so lots of small jobs run there, so that's expected. Woodchuck down here on the bottom is also another development type system. It's very low. It'll be moving into production soon, but you can see that we expect that. So this graph here looks pretty good to us overall. So with all of that as a background now I'll get into the interesting part, the actual problem. So we want to optimize for utilization, give people the most time that they can have on the system, but we have monthly maintenance scheduled for each of these clusters. Now this may sound crazy. On large clusters, this is actually the easiest way to do it. All of the work is scheduled in a ticketing system. We put it up on this calendar so everybody can see it. We have Monday stand-up meetings that we talk about the work that's going to be done and go ahead with the work. So maintenance, due to the way HPC systems are built, often affects an entire cluster at a time. This is a design trade-off that is made while designing a cluster. That network that I mentioned at the start, it's not good for jobs if you make that thing go away in the middle of jobs. You'll have something that may have been running for a week that will fail. So doing work on individual nodes, no problem. Doing things doing work on things that will affect the whole system, the OS image, the high-speed network, the file systems, it's safest to do with the cluster idle, and it's a known trade-off. So we want to mitigate this impact to users. We schedule similar clusters on different days. We do as much work beforehand as possible and only the idled cluster when we need to. So we try to keep the impact to users as minimum as possible. But it's still difficult to do that at times, and so this is where we've been looking at how can we plan this better. So looking at the impact to users, we're thinking, how do we measure that? And how do we use the info on measuring that to make stronger decisions? So looking at what's been talked about in this sort of conference for the last couple of years, there's been, error budgets, a good, useful idea that we look at, doesn't apply directly, but holding it up to our maintenance, it provides some inspiration. So that's where we started out. And so that brings us to the idea of what we want to do. A quick overview I know everybody in here knows what this is, but anybody watching the video later may not have a good idea. So a quick overview of what an error budget is, in my words. It's a nice way to hack your SLA to your advantage. So the basic concept, the SLA says 99.99% uptime is what you have to provide. That's actually 0.01% downtime. You can use that to your advantage to innovate, to fix, to do whatever you need to. Now, I said the exact implementation doesn't quite fit. If you have 0.01% of 10 million web requests, that's 1,000 requests. That's enough that you can try things out, do a little testing, get usefulness out of it. 0.01% of 1,000 HPC jobs is 1/10 of a job, which doesn't make sense, and it's not even clear that having a job fail is in any way useful to us. So the idea doesn't quite fit, but the idea of tracking and using it to our advantage does. And so we thought about, what do we do with that? So examining what we have, each cluster that we have has one 10-hour dedicated system time, DST we call them, scheduled each month. That's what we saw on the calendar earlier. So in one quarter, 3 DSTs times 10 hours comes up to 30 hours of scheduled downtime. So that gives us a budget there. In one quarter of the year, each cluster has 30 hours of downtime available. It's about 1.4% of the cluster's available time. We looked earlier and said that 80% utilization was pretty good, so 1.4% isn't too bad. Now this is something we can track now and use to make actual good decisions about what we're doing. So I'll talk a little bit more about what that means, but first some goals of doing this. We want to track the maintenance downtimes, see what we're using, see where we're going over or going under. We want to make downtime risk analysis easier so we can tell if we want to do more or less work during a certain quarter. We want to inspire teams to play along with this, to be able to play along with the metric and see if they can beat it or not beat it, and try to do better. And we want to report up our chain how we're doing. These systems are funded by various agencies. We want to be able to tell them we're doing a good job, we're doing a bad job, whatever it is for that particular quarter. We also have some not goals. We don't want to make things more stressful. We don't want to get into this mode of minute pinching or trying to figure out how to beat the system or becoming more worried about the metric than the outcome of it. These are all things that would make this useless and would be against the whole point of doing it. So we want to make this useful and helpful, not a terrible burden to everybody. So as an initial implementation, we wrote up some Python scripts, connects to a MySQL stats database that we already had existing, generates some JSON output, and it's graphed using Plotly. So no rocket science here. This isn't the impressive part, because anybody can sit down and do this in a few hours, in a week or whatever. Stats is still in the proof of concept because we're working on how we're going to use this information now, which is what I want to look at now. So here's a graph that this produces as our initial implementation. This is the most bare graph that you can have. It's Q2 of 2015, which is kind of old data, but it nicely demonstrates what I want to talk about here. Down in the x-axis, we have the dates running from April 1st over to June 30th, so Q2. On the y-axis, we have the number of hours are left in the budget, 0 at the bottom, 30 at the top. And the line here is the constant burn rate. If we were to somehow use the exact number of hours that we have allotted the entire time from 30 at the beginning to 0 at the end, this is what it would look like. So this is our baseline to compare against. So here it is with one graph, or with one cluster laid on top of it. And you can see exactly what's going on very easily. The cluster started out just running, having no maintenance. We came to the middle of April when it had its first downtime. It took, about 9 hours of its downtime, and so that dropped dramatically. And then got to the end of that, went for another month, came to the next downtime, used, 7 hours maybe. Ran well until the next one, used some number of hours again, and then we have the end of the quarter, and there's some time left over, maybe 6 or so hours left over at the end of the quarter. This is nice. This is not a visualization that we had previously. Now we can actually see better what's going on. We can lay another cluster on top of here. It didn't look so well. This one started out the same sort of way, following that constant burn rate line, all right, in a stair-step fashion. But then it had something go wrong. So this particular downtime, the high-speed network went down. We ended up keeping the cluster overnight without it running anything on it. And it burnt through all of its hours when nobody was doing anything until the next day when it came back up. And ended up, we didn't take any more maintenance that month because we'd taken up all of its time. Or during that quarter, we'd taken up all of its time. Ended up at maybe negative 13 or so hours. Again, this is a nice visualization of what this really looks like and how it really affects people in the real world. All of those systems that we saw earlier on that utilization graph, here they are plotted on top of this now. You can see that in general, everything's following that same stair step over the constant burn rate. And in general, we ended up with lots of time left over. That top one named Pinto, it took maybe 3 hours during that entire quarter and had all of this extra time that we could have used to do other things on the system. Here's another quarter, the quarter immediately after that one, where we didn't have such a good quarter. Again, they generally started out following the line. On about September 9th or so, we actually had a power outage that was planned. It was a facilities outage, we knew about it, but all of the systems were down, so everybody dropped down. We ended up going negative for that quarter, except for one system up there at the top. I'm not sure how it survived so easily. But again, it gives us a nice visualization to see what exactly happened during that time. So now the interesting part. What can we do with this information now that we have an easy way to visualize it, an easy way to think about what it means and what it's useful for? So in the most simple case, the very easiest thing that we can do is report on downtime budgeting. Well, do downtime budgeting and report on what it looks like. So this is the science tachometer, how many sciences are being created by the clusters at one time. We can report back to the people who give us the money to run the clusters, how we're doing, why we need more time, less time, whatever it is, to do these things. We can decide that we don't need 10 hours every month maybe if we're always below. We can decide that we need more time. But it makes it easier to actually start planning that. We can plan facilities work. So I mentioned before that there was a power outage that was one of that caused the big dip in one of those graphs. Those happen. That's how our power works. We sometimes, when we're bringing in a new cluster, that's actually what we see here is preparing to bring in a large cray system where we had to run water cooling under the floor. When we do these sorts of things, we have to shut down the power to the machine rooms for an hour or two at a time sometimes so they can pull new power into the building. And so using this, we can plan these things. We can sit down each quarter, sit down with facilities and say, what work do you guys need to do? How will that affect us? Let's budget that in, either add some extra hours or plan the time that we actually have is lower than that and do a better job of planning. We can plan for lightning strikes. So this is what a typical day or evening in the summer in Los Alamos looks like. Big thunderstorms roll in over the mountains and we get a whole bunch of rain and big lightning strikes like this. And maybe once or twice a year we'll have a machine room go down because of a lightning strike. So in the same sort of way as the facilities planning, we can look at this and say, okay, maybe we should add 2 hours to the budget during the summer so that we're ready for coming in and bringing things back up after one of these. We can also plan for dedicated user time requests. So we occasionally have people who ask for a few hours or a day maybe to run dedicated on one of the systems where they need to do something that requires the whole system or requires the rest of the system to be quiet so that they can do some benchmarking. And this we can use these metrics to decide, is this a good quarter to let people get on there? Did we already use up all of the downtime that we want to? Or is it all right to kick people off and get a dedicated user on there and it won't affect people's schedules too badly? And then there's the traditional idea of giving admins time to fix technical debt. So this helicopter here, if you live up in the mountains where there's lots of forests like I do, this is you may have seen these before. This is a helicopter that goes and puts out forest fires. So it gets filled up with water, it flies out, drops the water on the forest fire. So this, if you ever say, I'm gonna go put out a fire, this thing literally does that. And that's what we get. It's a nice metaphor for what we can give people time to do. Go out, put out the fires that are there, fix things that they wouldn't have the time to do normally. You know, if we have 3 hours at the end of the quarter, let's go take the system down for 3 hours to reboot those switches that we should have, or to do whatever maintenance there is. And so with all of that now, with all that said, I have a challenge for everybody here in the room, everybody at the conference really, but everybody here in the room is the people who hear it. And that's how can we generalize this. So I came from an environment that is not a traditional SRE environment. I took an idea that I know about from the SRE environment and mapped it to my world and how we could learn from that and make use of it. So there's a lot of SRE ideals that are easy to map to more traditional operations environments. Monitoring and metrics, clearly, if you go collect metrics, if you do better monitoring and you analyze those metrics, you're going to do better. Incident planning and analysis, everybody has incidents, everybody can sit down and do postmortems or retrospectives and analyze them and learn from them. Automation and configuration management, trying to automate as much as you can, everybody can work on that. But there are a lot of things that don't quite fit. Scalability, not everybody has hundreds, thousands, tens of thousands, millions of systems that they're managing. Imagine a small university that has, you know, a room full of desktop systems. That's not that huge of a scale. Hiring in the SRE sort of way, not everybody's a big web company that has name recognition that is that easy to recognize like that. Mikey Dickerson's gonna be here later this week talking about hiring into government, the same sort of thing. You don't have the ease of hiring at times. And continuous deployment is another good example of that. Not everybody has the time to continuously deploy things. Not everybody even has something to continuously deploy. So there's ideas that map easily, ones that map that don't map so easily. So my challenge is to look at what makes the SRE environments unique, you know, what makes each of your environments unique, and think about how can I teach this to somebody in a different environment? How can I teach what I've learned from my environment, how to do scalability, how to do all of these different things in a better way, how to automate better. Take it to somebody else, teach them how to do that in their environment. Now the important thing is, this is not a conversion or evangelization challenge. This is not go out and make people do things like I do them. The beginning of this talk, I described the HPC world so that everybody knew what that was. And then I described my problem and why I couldn't take an exact implementation that already is there and stick it into mine. This is the same sort of thing. This is a community building challenge of looking at what's going on out there, how can I help somebody else do better, and build their environment nicely. And so with that, that's all I have to say. I want to go out there, build that community, make it happen. If you have great ideas on how to do that, I want to hear more about them. There's my email and my Twitter handle. Love to hear about them. We can start talking about them right here with comments or questions. And thank you, everybody. Mm-hmm.
How do you then push that back up, because their overriding metric is always utilization or users and user service satisfaction. How do you bridge that back?
Yeah, so how do we get the metrics that we've gotten out of this and push them back up? So the Los Alamos is funded by the Department of Energy, and you know, it probably goes up deep chains there. So we start out at the local level. Our own management, what we report to them, how things look. And as it goes further up, you can imagine it gets a little bit more abstract at each level, what it is that you're reporting. So it really does come down to, as you said, utilization and how that looks. And it's always a challenge to turn utilization into something that really shows how the cluster is doing, because of the fact that there's 80% is pretty good. So you have to explain why there's why you're not going to see 100%, why things that are below 80% it maybe is all right, because maybe you are running all jobs that are 51% of the cluster, and therefore you could only run one at a time. So there's a lot of trading off that has to be done to push that up the chain and make sure that the right description of what's going on is going up with it. Yeah.
Hi. Yeah, I work in a small HPC center as well, so it's great to see your ideas here about the downtime budget. It's unfortunate that we're not a 24/7 shop, same as you guys. So 9 to 5. If the downtime goes past 5 p.m., that eats into your error budget.
Yeah.
It's pretty unfortunate.
So that's what actually one of the big things that inspired this is that for the clusters I just described here, they're all 9 to 5. So you come to the end of the day, and it's not like everybody says, "Oh, 5 o'clock, going home." People stay, but eventually you get to that point where you say, "This isn't part of what we're supposed to be doing. We'll go home. We'll come back in the morning and do it." And we had kind of thrown numbers around about what that actually looks like, but eventually we decided, let's graph that and see how much we're actually losing. And that's where it suddenly became clear, like that one graph, that we burned through an entire quarter's worth of budget just by having the machine down overnight one time. And so it became a bigger question then of, is it all right to let this go, or should we now start working? Should we stay here for the next 4 hours and bring it back tonight? Because it is the utilization, the availability to users that then really matters.
I wonder, would it be interesting to see a dual graph of just the 9 to 5 hours as well, and would that be useful as well? I don't know.
It might be.
Thanks.
Yes.
Hi, I had a question regarding the 10,000 or so nodes that you had. Like, are they all the same architecture? Are they all Linux x86, or do you have mixed architecture? And how often do you sort of turn over in terms of the machines, and how often do you
how often do we what?
How often do you add and remove clusters?
So the clusters are, there are about 20 of them I said there at the beginning. All of those are completely homogeneous, so they're all purchased at the same time. So we'll bring in a cluster of 100 nodes, 1,000 nodes, whatever it is, all the same. They will run as one set. We get spares and maintenance to go along with it so that we can replace them with the same kind of thing and then retire them all at once. So typically right now they're x86, 64-bit machines, pretty standard systems overall. In the past we've had some, well, I guess we currently have some with GPUs in them that make them a little bit different. We had some with cell processors a while back. But overall they're pretty commodity systems, except for that high-speed network. That's the thing that's usually different. It's InfiniBand, or Intel has OmniPath out now. Cray has their own crazy high-speed networks that they do. But in general, they're pretty standard systems. We tend to get a new cluster on average about maybe 1 per year, except for they all bunch up at the same time usually. So we'll tend to get 3 in 1 year and then nothing for 2 years after that, and then retire some. And it's this constant bringing in new ones, retiring old ones, preparing for the new ones, doing that facilities work to put in water cooling, et cetera.
Thank you.
Anything else? If not, thank you for sticking around.